Okay. Before I move on to the first example we're going to do, um, just like one thing in this picture that I forgot to write is that your normal vector does have to be a unit vector with appropriate orientation. And that'll be clarified when we write out the formal steps, and you'll actually see it in this example too. So, oops, I should actually write F in. So the example we have is that we're trying to compute the line integral of 1/2 y squared dy plus, dx, plus z dy plus x dz for C, the clockwise curve at the intersection of x squared plus 2y squared plus z squared equal 1 and x plus z equal 1. Okay, cool. Sorry, this was not clockwise. It was counterclockwise. I was trying to write this problem from memory. So I'm going to sketch what's happening first. I know it seems like I always recommend sketching and sometimes you don't need it, but in these problems, because we have this issue with the right-hand rule and all the potential surfaces you can select, I think it really does help to draw things. So I don't care what's inside the integral for now. I want to get a feeling for the curves and surfaces that I'm looking at. So just ignore whatever's inside the integral. Look at everything else you have. I've got this z squared equals 1 minus x squared minus 2y squared. And I've got this z equal 1 minus x. So this is going to be a bowl kind of thing. Let me swoop it back a little bit better so that you can be convinced it's centered at the origin, which it's not right now. So z squared equals 1 minus x squared minus 2y squared. We've worked with a lot. It's a bowl that starts up at 1 and then goes down in x and y. And z equal 1 minus x is going to be like a plane, kind of like that doesn't change in y, but z and x have this linear relationship. And then their intersection is going to be like, here, let me try to make that a little bit more skewed looking. So their intersection is going to be kind of this oval shape. That's a skewed slightly. All right. Lives in the plane, cuts through the bowl. So you can imagine you took the bowl and you cut through it at a slant somehow. And that's going to be our curve C, and it's oriented counterclockwise when we're viewing it from above. So this is counterclockwise, like that. So that's our curve C. And hopefully just seeing the setup for this has made you kind of think about the fact that if somebody gave you this problem, coming up with a parameterization for this curve would be quite difficult. Plugging it in and evaluating everything directly would be difficult. So that's why we want Stokes' theorem, because it's going to make this easier on us. So I want to use Stokes. And I have to go ahead and start identifying the things that go into Stokes' theorem so that I can use it. So the easiest is usually identifying F. So if I look at this line integral, just the different components attached to dx, dy, and dz are the components of my vector valued f. We saw that all these different representations of line and surface integrals really did relate back to their vector representation. And then I have to pick my surface. So my surface has to be something that uses as its edge my curve. And so when I look at this picture, I could pick like this part of the bowl right here, like I drew on the previous slide, that has that green curve as the base of it. But I'm going to find that it's easier to go ahead and use the part of the plane that's cut out by this circle. So I'm going to use S, the part of the plane, x plus z equal 1. That cuts through the bowl. And when I set up surface integrals, I know that my normal vector and my way that I write ds come from my representation of the surface as a function. So I better go ahead and do that right now. So I said z is equal to 1 minus x. That's going to be our f of xy, where we can go ahead and compute normal vectors in general are given by minus fx minus fy1, although they might not be unit vectors, so we'll have to fix that. And ds in general is given by dA times fx squared plus fy squared plus 1, all inside a square root. So we'll do those computations in a second. And then the only thing that would be left for us is we would have to figure out the region over which this integration occurs. And let's go ahead and do that after we compute a few things. So for my f equal to 1 minus x, I know that my normal vector formula in general, minus fx minus fy1, would give me minus 1, derivative with respect to x is minus 1, gives me 1 in the first component. No y's gives me 0 in the second component, and 1 is left. And so my unit vector that I can use in this Stokes theorem formula is going to be just 1, 0, 1 over the square root of 1 plus 0 plus 1. That's how unit vectors work. Blast from the past, I'm sure. But if they're rusty for you, just go back to that section. And then f equal to 1 minus x is also going to give me my ds equal to root fx squared plus fy squared plus 1 squared. Maybe you're seeing that that's exactly the same as what I got for normalizing my unit vector is square root 2 times dA. And then since I had f equal to 1/2 y squared zx, I'm going to go ahead and compute my curl. If you remembered the formula, you can do that the way that you learned. But I'm going to go ahead and do it with the determinant because that's easier for me. So I put d dx, d dy, d dz in my components of f, 1/2 y squared, z, and x. So I'm going to get I hat should be d dy of x, that's 0, minus d dz of z, that's 1. So I'll get 0 minus 1. I always remember to subtract my j hat. And then I'll get that that should be d dx of x, that's 1, minus d dz of 1/2 z squared, that's 0. Plus my k hat, that's d dx of z, 0, minus d dy of 1/2 y squared, that's y. So I'll get 0 minus y. So my del cross f is minus 1, minus 1, minus y. Okay, so I calculated the first block of things that I knew about. So my C of all that stuff, I'm not actually going to fill it in, I said would be equal to S of del cross F dot N ds. So I haven't figured out what to put on my bounds yet, but I just decided that my del cross F was minus 1, minus 1, minus y, I think. Okay, and my n is 1 over root 2, 0, 1 over root 2, right there. And then my ds is root 2 dA. I'm just signaling where all these different parts came from, where we calculated for them on this page. All right, and when I evaluate that dot product, I'm just going to get minus 1 over root 2 minus 0 minus y over root 2 all times root 2 dA. So that's going to be the double integral of minus 1 minus y dA when I simplify that root 2 over root 2. So in general, if you're using the n from this formula, n from this formula, it's just going to cancel out with the ds from this formula. The reason we make sure to check that your normal vector is a unit vector is just for when you have different ds, kind of like really simple problems where your unit vector just points in one direction, basically. Okay, so last part of this is we have to go ahead and set up our double integral to describe that we were thinking about this area here. So I'm going to go ahead and sketch again what we're thinking about. Thinking about this disk. It comes from cutting through z squared equal 1 minus x squared minus 2y squared. The bowl with the plane z equal 1 minus x. So since we know that intersection occurs when z equals 1 minus x and z squared equals 1 minus x squared minus 2y squared, I'm going to go ahead and set those two things equal. So we're trying to find this region R. So I know that z squared equals that, and I know that z is equal to 1 minus x. So I can go ahead and say root 1 minus x squared minus 2y squared is 1 minus x, or 1 minus x squared minus 2y squared is 1 minus x squared. Which looks like a mess, but don't worry, it's gonna be one of those nice completing the square problems eventually. All right, all of that should be like stuff that we did in the polar integral section, completing the square, just to tell us that this is a circle, radius 1/2, center at x equal 1/2, y equals 0. And that's the region we want to integrate over. And what we're going to have to kind of remember, I guess, from when we did polar coordinates, oh gosh, that's crooked, is that this is the circle I just picked. Imagine I was better at drawing it. This is the region R that we're trying to describe. And we learned in that section that this type of circle can be described by R equal cosine theta. So we could go ahead and set this up as what was inside our integral? -1 minus y. We can do this in polar coordinates. So we can say we're looking at r d theta is our dA. And our radius goes from 0 to cosine theta. And our theta will go from 0 to pi. And then our y will become minus r sine theta. We could go ahead and evaluate it there. But if this cosine theta thing didn't occur to you, it's okay to do the Cartesian coordinates. It'll just be a little messier. So instead, you would have gotten this complete the square. Wouldn't have hit you the same way. So you would just, at this point, have solved for y. And you would get, I'll write it here, y equals square root of, 1/4 minus x minus a half squared. You could do that. And it's going to be the plus and minus of that, of course. So you do from negative 1/4 plus x minus a half squared and plus 1/4 plus x minus a half squared. Copy that down right. And then those two things are going to be equal at x equal 0 and x equal 1. I cheated by looking at the picture, but you could go ahead and set these two things equal and solve for your x bounds. And at this point, it is the problem of just evaluating a 2D integral, just like we've been kind of reducing all the problems in this section that way. I feel like this is the only one you can solve on paper. This one, I think the x minus a half squared inside is going to present problems. So I would recommend this version.